Water is being poured out of a funnel at a rate of 15 cubic centimeters per minute. The right circular cone has a radius of 24 centimeters and a height of 32 centimeters. At what rate is the height changing when the volume is 12 pi cubic centimeters? So let's start by drawing a picture of this scenario. We have a right circular cone. And we're given some dimensions here. We're given the radius is being 24 centimeters and the height is 32 centimeters. So the radius here is 24 centimeters and the total height is 32 centimeters. And we now have water in this cone. So we're going to indicate the water level at a specific point in time. So the water level might be right here. And then we'll have the radius of the water level, or at the water level. And then we'll also have the height at the water level. Okay. They're also giving us a rate here. They're telling us that the water is being poured out of the funnel at 15 cubic centimeters per minute. So we're going to be referring to this as the volume that's being poured out. So that's going to be our dV dt, which is given to us. And because we are removing 15 cubic centimeters per minute, it has to be negative. And then they are asking us to determine the rate at which the height is changing at a specific volume, 12 pi cubic centimeters. So we want to determine dH dt when the volume is 12 pi cubic centimeters. So to determine the volume of a cone, we would use the following formula. Volume equals 1/3 times pi times radius squared times height. So the radius here refers to the radius at the water level, not the radius of the cone. Okay. Now this formula here will give us the volume as a function of the radius at the water level and the height of the water level. This is going to be a problem. We cannot have two independent variables here because we wouldn't be able to solve it. So what we need to do is we need to eliminate R by expressing or with R as a function of h. So we need to express the radius as a function of h, and if we can do that, then we can substitute that in here, and we're just going to be having one independent variable, namely the h. Okay. Now, if we take a closer look at the cone and the triangles that we'll end up with here, I'm going to sketch it again here. We have the total height of the cone. That's the radius of the entire cone. So this is just a slice of sideways sort of view slice of that cone. It is 32 centimeters tall and the radius up here is 24 centimeters. Okay, then the water level, that's going to be down here. So let's just say that the water goes up to here. That's your radius of the water level. We call the radius of the water level R. We call the height of the water level H. What we end up with are two similar triangles. We have the following triangle, which is similar to the following triangle. So that means we have similar triangles, and that will mean that the ratio of the radius and the height of the water level will be equal to the ratio of the radius of the cone over the height of the cone. And now we're able to rearrange this expression and isolate r. So r will now become a function of h, and we can reduce 24 over 32 to 3/4 times h. And now what we can do is we can now eliminate the r by substituting in that expression right there. So let's rewrite our volume formula. So we're going to get the volume equals to 1/3 times pi times radius squared, but radius is can be expressed as 3/4 times h, and that's squared, times height. We can clean this up a bit. We can square that 3/4 h. It's going to be 9 over 16 h squared times h. This 3 cancels, and we're left with a 3 up here. And now if we clean it up, we're going to get 3 over 16 pi h cubed. So that is our formula for the volume of the water. Now we need to differentiate it. So we're going to write dv dt equals the derivative with respect to time of 3 over 16 pi h cubed. Now 3 over 16 pi is just a constant, so we can pull it outside of the derivative. So we're going to get 3 over 16 pi, and then the derivative with respect to time of h cubed. We can now go ahead and differentiate. The constant stays. And we would have to use the chain rule here. So the outside derivative here is going to be 3h squared. And then the inside derivative is just going to be dh dt. Like that. So that's it. That is our derivative. We can clean it up a little bit. We can the 3 times 3 just to make it a little bit neater. So we can rewrite it as dv dt equals 9 over 16 pi h squared times dh dt. Okay, so what we want to do here now, we want to use this to determine the rate at which the height is changing with respect to time. In order to do that, we will need to know what the dV dt is. So at what rate is the volume changing? We know that. The question tells us that the volume is changing at a rate of negative 15 cubic centimeters per minute. So we have that value. We do not have the height. So before we can proceed here, we need to determine the height of the water level. So we're going to determine H at that volume, at the volume equals to 12 pi. It's just going to be cubic centimeters. Okay, like that. So to do that, we're going to just use our formula for the volume, this one right here, where we only have H, where R has been eliminated. So we can express this as the volume is 12 pi equals to 3 over 16 pi times H cubed, and then we solve it for H. So this is going to give us H cubed equals to 64, which equals to H equals to 4. And the unit there will be centimeters. So now we know H, and we can just go ahead and plug it into our differentiated equation. So we're going to get, so dV dt was negative 15 equals to 9 over 16 times pi. The height of the water level, we just determined that was 4 squared times dH dt. Okay. And right away we can see that 4 squared is 16, so this will cancel against this 16. Okay. And then if we rearrange it, we're going to get dH dt equals to negative 15 over 9 pi, which can be reduced to negative 5 over 3 pi. And the unit here will be centimeters per minute. So now we can say that the height of the water level is decreasing. So this rate here has a negative, it's a negative rate, which means it's decreasing. So the height of the water level is decreasing at a rate of 5 over 3 pi centimeters per minute.